2. Describing wave motion. When particles are set into vibrations by the wave successively, they have a common amplitude, period, and frequency. Their amplitude, period, and frequency follows that of the wave because it is the wave that sets the particles into vibrations. Let's see how we define amplitude, period, and frequency of a wave, and also see the meanings of wavelength and wave speed. For simplicity, we will focus on transverse waves first. A. Amplitude. When a transverse wave travels, we can take a snapshot, that is, a photo. The snapshot of a wave shows its waveform, the shape of the wave, just like figure 4.2d. The amplitude can be measured directly from the snapshot, from an equilibrium position to its crest of a transverse wave. For a sinusoidal transverse wave, the amplitude measured from an equilibrium position to its trough should be the same. Amplitude is a measure of energy of vibration. The energy of a wave is directly proportional to the square of its amplitude. This means when the amplitude of a wave is doubled, the energy of the wave increases by 4 times. B. Wavelength. It is the minimum length that the waveform repeats itself measured in meters. For a sinusoidal transverse wave, the wavelength equals the distance between two successive and therefore laboring crests or troughs. Of course, you may measure the wavelength of the wave using other parts of the wave, as shown. For other waves, which is non-sinusoidal, such as this, you can still measure the wavelength. C. Period. Period of a wave is the time to generate a wave from the source. Well, it is also the time for the complete vibration, as you can easily deduce. Moreover, in 1 second, the wave should have traveled forward by 1 wavelength and traveled by 2 wavelengths into periods and so on. In this way, the wavelength lambda equals the wave speed multiplied with the period t. Example 2. Sketching waveform. You are given the waveform at t equals 0, and you are asked to draw the waveform sometime later, which is actually a quarter of a period. So the waveform should have traveled a quarter of a wavelength to the right. So you should draw a sketch to the right, moving a quarter of a wavelength like this. D. Frequency. The frequency of a wave is the number of complete cycles of wave that is generated in 1 second. Obviously, it is also the number of complete vibration completed by the particle in 1 second. If the frequency of a wave is 2 Hz, 2 complete waves is generated in 1 second, and hence each complete wave takes 0.5 seconds to generate, and the period is 0.5 seconds. And therefore we have F equals 1 over T for wave frequency F and wave period T. Well, interesting. The frequency and period of a particle vibration also have similar relationship, and you can also see we use the same symbols F for both frequencies and T for both periods. In fact, the frequency of a particle vibration and that of a wave are different in definitions, but same in value. Similarly, the period of them are differently defined, but their values are the same too. That's why people often mix them up, and we may hardly find any case that they are different in values, although they have different definitions. Example 3. Finding amplitude, wavelength, and frequency. Figure 8 shows the waveform of a water wave. We can measure the amplitude and wavelength directly from the snapshot. And for the frequency, easy. Let me leave it to you. E. Wave speed. It is the speed of wave. It is how far the wave may travel in 1 second. As a wave travels a distance of 1 wavelength in 1 period t, the wave speed is thus lambda over t, and thus V equals F lambda, which applies to all kinds of waves. Example 4. Finding wave speed and applying V equals F lambda. It is a simple application of the above formula. Let me leave this example to you. Try check point 3 below.